So this is work again of a fairly large collaboration. These are the main people on it, but there are in fact quite a bit more. And what we're trying to do is to model the active regions on the sun. So this is an image of coronal mass ejections. And this is why it's important, because these are the explosions from the sun that accelerate protons and electrons to very high speeds, which then impact the Earth. And we don't know the whole process of how this happens, but we know that it's basically has to do with the magnetic fields, and the magnetic fields are produced by dynamo action inside the sun. So the process is that you have a turbulent dynamo that's acting inside the sun. That produces the magnetic fields, which then emerge through the surface. They show up as sunspots and pores. And as new magnetic field emerges, it interacts with the existing magnetic field. It produces flares and these coronal mass ejections. It accelerates the energetic electrons and protons. They reach the Earth. They are what produce the aurora. They affect radio communications. They have been known on occasion to actually bring down the electric grid. They'll affect the GPS system, and they can affect the satellites. So that's why we're doing it. So the way our project is started is we're not doing the whole global dynamo simulation. We're looking at the effect of magnetic field near the surface of the sun on the magnetic field that's produced by the dynamo. We're also looking at the surface dynamo. And what we do with this magnetoconvection simulation is that will give us boundary conditions for simulations that will then model the chromosphere and the corona and these other complex things, and calculate the acceleration using several other different codes, but using the input from the code that I've been running, the stagger code, as bottom boundary conditions. So the stagger code is a finite difference code with 6-order finite differences on a staggered grid with 5th-order interpolations. It uses a stretch grid in the vertical direction. Resolution varies between about 12 kilometers at the surface and about 80 kilometers down near the bottom. We use a 3rd-order Runge cutter with a compact storage thing for the time advance. Since we're trying to actually compare things with what we really observe on the surface, and we try and make the physics as realistic as we can, so we're using the tabular equation of state, but since we're only interested in the photosphere and below, where the collisions are high, we can assume that there's local thermodynamic equilibrium, which cannot be done up in the chromosphere and the corona, which is why those other codes, some of which are similar to this, but they have other physics in them, so they can do the non-equilibrium thing. But the equation of state we use does include excitation and ionization of hydrogen, helium, and the other abundant elements. The crucial thing we have to do is to actually do the radiative transfer. We can't use the various approximations that people tend to use in other situations for the radiative transfer, because then you won't get something that really looks like the sun, nor will you get the driving of the convection properly, because the convection is being driven by the energy loss from the surface, which is producing you large entropy differences because of the cooling of the fluid, and so you have to get that right with the radiation. So we're doing 3D radiation, we're assuming local thermodynamic equilibrium, we're doing the long characteristics, and we're using a 4 to 12 bin multi-group for the frequency spectrum. And we use what we call quenching, which is a sort of hyperviscosity, where we take the actual Navier-Stokes expression for the diffusion, but for the viscosity coefficient, we enhance it by the ratio of the third differences to the first differences for the function, so that it enhances it where there's wiggles and reduces it where it's smooth. So the key challenge here is to do the radiation. Radiation, it's inherently three-dimensional, and it's non-local, so it couples wide distances, so there's a lot of communication, and we're using these long characteristics which fill the volume, And so we need to communicate volume data. And so the way to reduce that communication is to restrict the transfer only to the very surface layers where it's really important. And where you go down deep, the radiation is very unimportant, and in fact, the numerical diffusion in the energy equation would be larger than the radiation anyway, so one might as well neglect it. One of the things that we've been working on for the future is to split up the processors on given nodes so we can do the radiation separately from the hydro simultaneously, and possibly even be able to put the radiation on the GPUs. And this will allow us to use larger domains, so there'll be less communication. And this is the strong scaling we have at the moment. Previous to this, we've been running on Pleiades at NASA Ames. And Pleiades is about 2.5 times faster than Blue Waters, but we can use 4 to 8 times as many processors so far on Blue Waters, so we get a significant speed up, and we're doing an evolutionary calculation, so we have to do many time steps to see how this all evolves. And we've been doing 2 different simulations of the surface magnetoconvection. So our basic setup is that the inflows at the bottom of the domain advect in magnetic field. And so far we've been assuming that it advects in uniform, horizontal, untwisted magnetic field of some fixed strength. And so the variables are the size of these inflow domains, which is controlled by the convection, and the strength of the field that we assume. And we're running 2 simultaneous calculations. One is we're trying to extend our domain, which is now 96 megameters wide by 20 megameters deep. We want to extend it down to a 30 megameter depth because the people who do the interior calculations can't come all the way to the surface. They can come up to about 20 megameters, but we want to take their results not close to their boundary because the results are influenced by exactly what they assume for the boundary conditions. So by going down to 30 megameters, we can use their data on the magnetic field strengths and the sizes as input to the magnetic boundary condition in ours. And also we'll then have larger convective cells, because as you go down deeper, the temperature goes up, so the scale height goes up, so the size of the convection goes up in proportional to the scale height. And the second thing that we're doing is we're actually looking at a surface dynamo to see what its effect on the active region formation will be. So to give you an idea of what we do, so the arrows are showing you, this is a slice, the arrows are showing you the velocity field, and the color is showing you the magnetic field strength with the scale there on the side. And you can see that the upflows are bringing up the field. There is some buoyancy effect, but it's not very large. And the field comes up to the surface, and then we get these structures. And you can see that near the top, things are evolving very rapidly, but as you go down deeper, they're evolving much more slowly. And here you have a flux tube that has been formed automatically by the convection, and that's produced one of the, in this case, it's more like a pore because it's small. This is a region that's only 48 megameters wide, but and if you did this on a larger scale, it would be a sunspot. And one of the things we're trying to understand is how this process occurs. So what we try to do is to follow individual field lines. And so here you see there's this loop which is coming up towards the surface, and we're doing the best we can to follow the field lines as time goes on. Can't do it very well, but we can get the overall picture. There is some field lines that do jump around some because it's hard to follow the individual field lines. But you can see how the large-scale loop comes up to the surface. It gets shredded by the convection as it's coming up to the surface. And so it first goes through the surface in this very mixed polarity kind of thing. But then the small-scale stuff goes up into the atmosphere, and you're left with the legs of this large-scale loop, which are then the feet of the bipole, which is forming the active region. And since we're not putting in this structure to begin with, you can see that they have different structures, that one of these is fairly coherent all the way down. The other one breaks up into several different pieces, and they're all fairly twisted. And this is very much like what one sees. This is a movie of the actual observations of the sun, where you're seeing the black and white are the opposite polarities of the magnetic field, and it comes up with a mixed polarity here in the middle, and then they separate into the more coherent flux tubes at the end. And that's very similar to what we see. It's a little bit hard, I guess, to see this with the light. But so the green here is horizontal field, and the red and blue are the different polarities of the vertical field. And so you're seeing that it's coming up here with mixed polarities, and they're getting separated into the opposite polarity concentrations, where they're forming these mini sunspots. And here's a second big loop which is coming up. And again, it comes up with the mixed polarity in between, and then they separate into the two opposite polarity concentrations due to the large-scale loop structure from below. So in these two things that we've been running, what we did to extend the 20 megameters down to 30 megameters is that we extended it with a quiescent constant entropy hydrostatic extension, and the convective motions then penetrate in from above, and it has to relax thermally. So far it's run about 8 1/3 hours, and when it finishes relaxing, we will double the horizontal extent from 96 to 192 megameters, which will be able to really encompass the size of a real solar active region. And because it's deeper, we'll also have larger scale structures at the bottom. At 20 megameters, the size of the structures at the bottom are about the size of small supergranules, somewhere between 25 and 30 megameters. But as we go deeper, we expect to get larger structures. So what we find so far is that the entropy indeed is constant down at the bottom, as it should, but the convective flux is slowly relaxing. So these are the different times since the beginning, and had better eventually end up flat at the solar value. The other simulation that we're running is the surface dynamo. So this is the total energy, and there are jumps where we've either decreased the diffusion or increased the resolution. It's beginning to saturate a little bit up here. It's reached about 2.5% of the kinetic energy so far, and it's still going up. And if you look at it, what's interesting is that this is the kinetic energy density. These are the magnetic energy density at different times. This is at 3/4 and half and 1/4 of the time since we started this. And you can see that they're all basically power laws in the density, but that as the time goes on, the magnetic field strength has been increasing. The kinetic energy density has stayed more or less the same. And the pattern of the magnetic field follows the convective pattern. So the field tends to be concentrated in the downflows, and also, as you can see from this view from the top, and it also, you get, as you saw on the last slide, you get the stronger fields down here towards the bottom. And if you look at a blow-up of this, you see that there's this really complicated turbulent structure to the field which is being produced. This is a local dynamo. We're not making a large-scale dynamo here. We're just taking a little piece of the surface of the sun. And there are places where there are strong fields which have emerged through the surface here. And so we're getting locally kilogauss fields at the surface, which is what you need for the active regions. But they're still very, very small compared to that. So to summarize, we've been running on Blue Waters on between 32 and 64,000 nodes to model this active region formation. We've been extending the depth and eventually the width so we can accommodate realistic solar active regions. In addition to that, the same data has already provided synthetic data to people who are doing helioseismology to test their analysis, their inversion procedures, particularly in magnetic regions. It also will provide synthetic data for the new solar telescope at Big Bear in California and for the new Inouye Solar Telescope, formerly the ATST, which is being built in Hawaii, will come online in a couple of years. The other parts of this project, for the chromospheric and coronal part, has to wait until this part is finished. So they will hopefully start sometime next year. And this is a picture of 3 of these magnetic concentrations that have formed. Something's going on with the bulb in the projector. And you can see that they have very different structures. So there's this wide range of structures that you get, and so our intention is sometime in the future, not part of this particular PRAC, that we will look at several cases of formations of active regions, so we can begin with different magnetic field structures, so that we can see something about what the range of the subsurface structures are, which is important for doing the helioseismology on them. Thank you.
We do have time for a few questions.
I missed this, but what were your boundary conditions on the magnetic field at the top?
At the top, we make it go to a potential field.
You said you're doing the radiative transfer in the surface region, and does that give you a large load imbalance, or is that sort of a static imbalance that you could deal with? How does that?
That is somewhat of a problem, and but it uses the process pretty well. The imbalance came because of the communication. Everything waited on the communication, which is why we've tried to reduce the communication as much as we can. And so the current idea is to do them on somewhat different sets of processes. We'll have to then statically fix the load balance after we find out what it is.
Yes, right.
And it'll probably be different for different numbers of processes, of course, but we can figure that out on small, short, tiny runs.
Yeah.
And then they'll happen simultaneously, and because since it's an explicit thing, you just take all the data, ship it up from the hydro to the radiation, they'll both do their stuff, and you ship it all back to the hydro to do the advance in time. So that should work pretty well, and we've had some discussions with the people here and with Nordland, who's doing a lot of the coding, one of the co-Is, and it looks like it's actually a fairly simple process to split the MPI.
We have time for one more brief question. All right, well, let's thank our speaker again.